this episode, we are going to solve examples based on the energy balance equations that we wrote. So we have our first example. Let's look at it. A rigid tank contains a hot fluid that is cooled while being stirred by a paddle wheel. Initially, the internal energy of the fluid is 800 kJ. During the cooling process, the fluid loses 500 kJ of heat, and the paddle wheel does 100 kJ of work on the fluid. Now, determine the final internal energy of the fluid. Neglect the energy stored in the paddle wheel. Are we good? So we have this rigid tank. The rigid tank means it was a closed system. Are we good? This is a closed system. And we are given the various parameters or energies. So let's list down our parameters. First, the initial internal energy of the fluid is 800 kJ, meaning there's an initial and there's a final. So I'll say my U1 internal energy is represented by U. So my U1 is 800 kJ. Pay attention. During the cooling process, the fluid loses 500 kJ of heat. So there is heat loss, which was heat out. Are we good? 500 kJ. And the paddle does 100 kJ of work on the fluid. So this paddle, looking at the system, this paddle is doing 100 kg work on the fluid. So anytime work is done on the fluid or on the system, it is work in. That is work in. Anytime work is done by the system, it is work out. So the paddle is doing work on the fluid. So we are working on it. So that will be work in. So we have work in to be 100 kilojoule. Now determine the final internal energy. I told you we have initial, so we are going to determine the final, which will be U2. Should be what? So these are our parameters which will help us solve the question. Now we have heat, we have work, we have initial and final internal energy. Do you remember this equation? The energy total within any system is the internal energy plus the kinetic energy plus the potential energy. Are we good? So we are going to use this equation and let's make some deduction. From the question, the tank is rigid, and a rigid tank means it is stationary. And we learned from our previous lessons that anytime a system is stationary, meaning kinetic energy, the velocity will be zero, meaning kinetic energy will approach zero. Then change in height too of the system is constant, which is, so there's no change in height, making potential energy go to zero. So we can have our E to be equal to our internal energy. And now from the question, we are seeing change in internal energy, meaning our change in internal energy U will be the same as change in E. Are we good? Alright. And we also know that when heat and work are involved in a system, the equation for it is, so first we've established that the change in the U is equal to the change in the total energy from this equation. That's one. We can also know that from the second equation, we know that change in E, do you remember this equation is, we have heat in minus heat out plus work in minus work out plus energy of mass in minus energy of mass out. Do we remember this equation? Alright, so now since change in energy is also equal to change in internal energy. Since the system has no potential and kinetic energy, can we equate the change? So if I'm representing the change, that will be U2 minus U1. U2 minus U1 equal to the same thing. I have Q in minus Q out. But if you know, you can just go straight forward to the this equation. But I wanted you to understand, that's why I prove it from this point. Plus work in minus work out, then plus energy of mass. This is the general equation. Energy of mass out. Are we good? So this is the equation we are going to use. Let's ask some questions. Within our parameters and within the question, was there heat exchange? Yes, there's heat exchange. So it will maintain. Was there any work? Yes, work was done, so maintain. Was there any change in energy? And remember, change in energy of mass. This is a closed system. So the only thing that can get out and in is work and heat. So meaning the whole of energy of mass goes to zero, because there is no energy exchange or energy of mass exchange. This is a closed system. Assuming it was open, then this would be needed. So now our final equation will be U2 minus U1 equal to Q in minus Q out plus work in minus work out. This went out because this is a closed system, no mass exchange. So now we have this. Let's do some deduction. Within the question, was there any initial or final energy? That's what we are looking for. So U2 will count. Was there any initial energy, internal energy? Yes, U1, we got it. Was there any Q in, which is heat added to the system? No, there's no heat added to the system, meaning Q in will also go to zero. There's no heat addition. Was there any heat out from the system? Yes. So it will maintain negative heat out. Was there any work in? Yes. Work was done into the system. Was there any work out within the system? No. So work out will also go to zero. So now our final equation, U2 minus U1, is equal to negative Q out plus work in. So this is our final equation. Now we have all the parameters. Let's put it in and find our U2, which is determine the final internal energy. So U2 now will be equal to, this will cross the sign. The Q out was 500, so that will be negative 500 kilojoule. Now the work in positive is 100, positive 100 kilojoule. When this internal energy crosses the equator to be positive, so positive 800 kilojoule, meaning our U2 now will be 400 kilojoule. So from this question, the final internal energy of the fluid will be 400 kilojoule. And does it make sense? Yes. Let's first start. Initially, I had the intent. Let's forget about the equation. Let's make some deductions. The initial internal energy of the system was 800. Are we good? My system had 800 kilojoule. And throughout cooling process, it lost 500. So it lost 500. So I'm having how many now? I'm having 300 now. It has lost 500 due to a heat loss. And a paddle also does a work of 100 on the fluid, but there was an addition of work, 100 work done, meaning the final energy now will be 400. So you see, it makes sense. So this is our final U2. Our second problem. A room is initially at an outdoor temperature 25, this is degrees Celsius, 25 degrees Celsius. Now, a large fan that consumes 200 watts of electricity when running is what turned on. The heat transfer rate between the room and the outdoor air is given as that, where U is given this degree Celsius, is the overall heat transfer coefficient. A within the equation is 30, this is meter square, is the exposed surface area of the room, and Ti and T0 are the indoor and outdoor air temperature respectively. Determine the indoor air temperature when steady operation conditions are established. This is very simple. Let's break down the question. Now, our outdoor temperature, which is represented by what T0, can be, so listing the parameters, our T0 outdoor temperature is given as 25 degrees Celsius. Are we good? Then now a large fan consumes 200 watts of what? Electricity. So this fan is consuming what? 300 watts of electricity. And what is what? Work. And is it work in or work out? Because the fan is what? Consuming. We are giving it to what? The fan. So it is consuming from us. Work inside the fan. Are we good? It is consuming from our electricity. So work inside the fan. That is work in. To be what? 200 watts. Are we good? Now the heat rates between the room is given as this. Now the heat exchange is now given in an equation form. So the Q out, Q in is now given in what? An equation form. So we have our Q to be U this way. This is Ti minus T0, where U is given as 6 watts per meter square, and our A within the equation is given as what? 30 meter square. Now determine the indoor air temperature when steady conditions are what? Established. So now let's make some assumptions here. Remember, thermodynamics is made of assumptions. It's a fan. We have a fan that is consuming this amount of electricity. If there is what? Steady operation condition, the fan is steady, meaning whatever electricity we are giving it to the fan is coming out as what? The heat. Is that true? Yes, because energy is never what? Created nor what? Destroyed, but changed from one form to what? The another, meaning the electricity given, electrical energy given is now converted to what? Heat energy, everything. So we can say the heat produced by the fan is now equal to the electricity what? Consumed. Is that true? Yes, that is true. So now we have our heat equation. We can say that our work in is given as the heat what? Is equal to the heat exchanged, which is also equal to what? Q. So meaning this 200 is the same as what? Our Q. But what is Q? We have the equation given. So I have Q to be U, that's Ti minus T0. So we have all our parameters. We are looking for what? Determine the indoor air what? Temperature. And what's the indoor temperature? Ti. So making Ti the subject from this, what do we have? We are going to have Ti should be equal to what? Q on UA plus T0. Do we have them? Yes. So I can do my substitution, where Ti indoor temperature is equal to my Q, 200 on U. We have U to be what? 6 and A to be 30, and our outdoor temperature was what? 25. You can work in Kelvin, but still you get the same answer, 25, and our Ti will be given as what? 26.1 degree Celsius. because of the Celsius we worked in, the answer should be in what? Degrees Celsius. Are we good? So meaning the outdoor temperature is 25 and the indoor temperature is 26.1. What you have to know here is that the fan is consuming this electricity, and since there is steady operating conditions, all what we give to the fan in terms of electrical energy is given out as what? The heat energy, and we can equate the parameters. Our example 3 is very simple. You see, thermodynamics is very simple. Water is being heated in a closed pan on top of a range while being stirred by a paddle wheel. During the process, 30 kJ of heat is transferred to the water and 5 kJ of heat is lost to the surrounding air. The paddle wheel work amounts to 500 watts Newton meter. Determine the final energy of the system if the initial energy is what? 10 kilojoule. This is similar to the example 1. Are we good? So let's get the parameters. So water is being heated on what? A closed pan. So this is what? A closed system. It is closed pan. So no energy of mass what? Exchange. Closed pan. During the process, 30 kJ of heat is transferred to the water. Heat is transferred to the water. That will be what? Yes, heat in, right? Yes. 30 kJ was transferred to the water. Then 5 kJ of heat is lost to the surrounding. That will be heat out. It's lost. 5 kJ. Are we good? The paddle wheel, look at the diagram. Always the diagram will help you. So during the heating, 5 kJ was what? Moving out. 30 kJ was moving in. And there was a work done of what? 500 Newton meter. So work done is done by the paddle on the system. So we are doing work in. We are working inside the system, which is 500 Newton meter. And 500 Newton meter is the same as what? 0.5 watts kilojoule. Are we good? This is the same as 500 watts joules, which is the same as 0.5 in terms of kilojoule. I hope you get it. All right. So we have the paddle. We determine the final energy. We are to determine the final energy, which is U2 internal because it is closed. We don't know. If its initial energy is 10 kilojoule, so our U1 is given as what? 10 kilojoule. Are we good? So can we write down our equation? Since it's a closed system, I'll just go straight forward. But we've already established that our change in what? E is equal to what? Change in what? U. And we know that our change in E for a closed system energy analysis involving heat and work will be what? Heat in minus what? Heat out plus work in plus minus what? Work out. No energy of mass because it is a closed system. And the change in U was U2 minus U1 equal to Q in Q what? Out plus work in work out. Let's bring in our parameters. Was there any heat in within the system? Yes. Any heat out? Yes. Was there any work in? Yes. Any work out? No. So work out will go to what? 0. Are we good? So our U2 now, which is the final energy, will be U1 will cross. So we have Q in minus Q out plus our work in remains. And U1 will also, because work out is going to 0 plus our U1. And U2 will be Q in is what? 30, Q out 5. Because you cannot work in 500 Newton meter, you have to change it to joules, And because this is in kilojoule, you also convert it to a kilojoule. Pay attention to that. 0.5 plus our U1, which is what? 10 kilojoule. This will give us what? 25 plus 0.5. They are all in what? Kilojoule. Plus what? 10. All in kilojoule. So final answer will be what? 35.5 kilojoule. Are we good? So within the system, our final, after the operation, after the heat gain, heat loss, work done, the final energy of the system will be this 35.5 kilojoule. Let's make our general analysis if it was to be objectives. So now, initially I had a system of what? 10 kilojoule initially. And when I was doing analysis, 30 kilojoule of heat was added. My system was already there with initial energy of 10. Heat of 30 was added, so plus 30. I'm getting what? 40 now for the system. Then 5 was lost, minus 5, giving me what? 35. Then work is done, 500 Newton meter. Converting it to joule will be 500 what? Joules, because Newton meter is also the same as what? Joules. And these are in kilojoule. I'll convert 500 joule to kilojoule, which is 0.5. So 0.5 work was done on the system plus 0.5, and I'm getting 35.5 kilojoule. Are we good? Our final example. You see, it's very simple. Let's look at how best we will solve this question. They are not difficult. A fan that consumes 200 watts of electric power when operating is claimed to discharge air from a ventilated room at a rate of 1 kilogram per second at a discharge velocity of 8 meter per second. Determine if this claim is reasonable. Now we are there. Someone is selling this fan, and these are the claims the person is making, that if it consumes 20 watts of electric power, it will give us air rate at what? 1 kilogram per second at a velocity of 8 meter per second. So as an engineer or as a student, determine if it is true with these parameters given. So with the idea of thermodynamics, we are going to see if it is true. Are we good? So first we will make our analysis. Since the fan consumes 20 watts of what? Electric power, meaning work is done inside the fan. We are working into it. Are we good? We are putting work which is 20 into it. 20 watts. So now, when operating, it discharges air at a rate. So we are talking about rate. So the mass rate is what? 1 kilogram per second. And the velocity is also 8 meter per second. Let's write our energy analysis equation. When a rate form is given, do you remember when it is in a rate form, the E dt is equal to the same energy change. We have Q in, Q out, plus we have work in minus work out. Is there any energy of mass in? Yes, look at the fan. It's an open system. It's an open what? System. Air is going out, can come in. This is an open system. So energy of mass is what? Exchange. So energy of mass in minus energy of mass out. We have this equation. All right, let's make our analysis again. Within the question and within the parameters, was there any heat exchange? No. So all this heat exchange will go to 0. Are we good? Was there any work in? Yes, we have it. Any work out? No. no work out, yes, so it can also go to what? 0. So let me break down the equation now. I have the E on the T to be equal to, all the heat exchange is gone, no heat exchange. I have my work in, I have plus energy of mass in. Will energy of mass out go to 0? Yes, or let's see, energy of mass out. So these are the 3 parameters left. One should go. Looking at a fan from the question and looking at the diagram, the energy of the mass, so the air is the mass now. Is it coming inside the fan or it is leaving? It discharge air. So energy of mass is what? Out. So meaning energy of mass inside is also going to 0. So the equation is now limited to the E dt work in minus energy of mass out. Are we good? All right. So let's look at this. Energy of mass what? Out, work in. The E on what? The T. So if, let's pay attention, if energy of mass is out, then what form of energy is the fan bringing out as the air is moving? Kinetic energy. Is that true? Yes, because as the fan is blowing the air, they are moving with what? Kinetic energy. So the energy of mass that is out is what? The kinetic energy. And let's pay attention here. If the rate of what? If this fan is in equilibrium or at a steady state, then the E, the T, the rate of the energy what? Exchange, work in minus energy out should be giving us what? 0, because it is what? A steady. Are we good? Is this, if this fan is what? At a steady state, then our work in minus our work out should be equilibrium, should be 0. Is that true? Yes. Then we can also rewrite our equation as energy of mass, because at, if this fan is at 3, it will blow at what? A steady state. Are we good? The energy given is the same as energy what? Given out. So steady, meaning energy of mass out is the same thing as what? The work in. The work you are giving, the electricity work you are giving is the same as the mass you are also what? Giving out. So this is what? Established. If it is steady, and yes, the fan is going to be steady at what? A particular state. If it is 3, if it here is 4, a steady 5. Are we good? So this is established. We now know that the energy of mass that is coming out is in the form of what? Kinetic energy. And what is kinetic energy? Kinetic energy is giving us half the mass times the velocity squared. So can we replace the energy by the kinetic energy? Yes. So I can have my half mv squared equal to my work in. So I want to see if this claim is reasonable. I want to check if indeed this fan will give us this velocity. Now I have the parameters. Let me check if the person claiming the fan discharge a velocity of 8 meters per second is true. So I'm solving for the velocity. So making the velocity the subject from this equation, you are going to have velocity should be equal to what? The work in multiplied by what? 2 divided by the mass, then the square root of it. Putting in the parameters, you have your work in to be what? V square root of 20 multiplied by 2 on the mass 1, and our V is giving us 6.32 meter per second. So is the claim reasonable? That's false. So the person is not telling us the truth. The fan can only discharge at a velocity of what? 6.32 meter per second square, or meter per second is velocity. So the claim is not what? Reasonable. I can also check with the mass from this. Let me check if the mass is also going to be 1. So making the mass the subject from this equation, what am I getting? I'm getting mass to be equal to work in multiplying to on what? The velocity square, which is m So that will be 20 by 2 on velocity square, which is 8 square. And I'm getting the mass to be what? 0.625 kilogram per second. And indeed, the mass is also not up to what? 1 kilogram per second. So the claim is not reasonable. Are we good? Thank you for watching this episode. This is the first set of problems. Check out for the second 4 set of what? Problems.